Linear Algebra Chapter 2. Now let's get into matrices. So matrices, definition and types of matrices. As a definition, a matrix is a rectangular array of numbers, symbols, or expressions arranged in rows and columns. It is usually enclosed within square brackets or parentheses. A matrix has m number or having m number of rows and n number of columns is called m times n matrix, meaning it has m rows and n columns. So let's say, given this example where you have A is equal to 1, 2, 3, 4, 5, 6. So m is equal to, which is the number of rows, correct? And n is equal to 3, which is the number of columns. First column, second, and third. So this is a matrix of 2 rows and n equals 3, which is 3 columns. Different types of matrices. You have row matrix, only one row, which is very similar basically to a vector. Example 1, 2, 3. So one row, despite the fact that it has 3 columns. Column matrix, so designated by one column, the same as simple vector, except it is only a column vector. Okay, so one column but multiple rows, like 6, 7, 8 here. Square matrix, where the number of rows is equal to the number of columns, or m equal n, like in the following example, where you have 2 rows and 2 columns. Okay, so let me draw it. First row, second row, correct? And 2 columns, also 1, 2. Zero or null matrix, all elements would be 0. For example, 0, 0, 0, 0. Diagonal matrix, where all non-diagonal elements are 0. Diagonal elements may be non-zero. For example, here, only the diagonal elements are or can be non-zero. So you have 5, 2 minus 8. You might have, for bigger matrices or for like a matrix like that, even some of the elements in the diagonal are 0. But the thing is, the essential, like the necessary condition is that only the diagonal elements can be non-zero. All the other elements within the matrix are definitely 0 all the time. Scalar matrix, a diagonal matrix with all diagonal elements equal all together. So all the diagonal elements are equal to each other. This is only used for scaling, like K. How we've seen K for ordinary simple vectors. K is used for scaling, to scale the matrix, like to augment or increase the magnitude. The same way here, a scalar matrix has the role to augment or increase the magnitude of a vector. Okay, it has the same number value within the diagonal, and it's used to scale up or scale down the matrix that it would be multiplied by. Identity or unit matrix, a square matrix with 1 on the diagonal and 0 elsewhere. Example, I3 is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. So you have only 1s on the diagonal and 0 elsewhere. Upper triangular matrix, where all the elements below the diagonal are 0. For example, this one. Lower triangular matrix, all the elements above the diagonal are 0. Matrix addition. Matrix addition is the operation of adding 2 matrices of the same size by adding their corresponding elements. So let A be equal to Aij Mn, B equal Bij Mn. Then their sum, C would be equal to A plus B, is defined by Cij is equal to Aij plus Bij, meaning you add different coordinates, okay, different elements, each one at a specific position with the one from the other matrix at the same position. Okay, so for all I equal 1, 2, all the way to m, which is the number of rows, and j equal 1, 2 all the way to n, which is the number of columns. For both matrices to be eligible for addition, they must have the same dimensions. So n should be the same number of rows and same number of columns. Example, A equal 2, 4, 6, 1, 3, 5, B equals 7, 8, 4, 8, 9, sorry, and 4, 0, 2. You notice that for these two matrices, both of them have 2 lines and 3 columns. Since both are 2 times 3 matrices, having 2 lines and 3 columns, then we can add them element by element. So A plus B is equal to 2 plus 7, then 4 plus 8, then 6 plus 9, 1 plus 4, 3 plus 0, 5 plus 2, which gets us 9, 12, 15, 5, 3, 7. Properties of matrix addition. Commutative, so A plus B is equal to B plus A. Associative, A plus B plus C, which is adding 2 matrices, and what results from that would be added to the third matrix C, is equal to A plus, adding A to B plus C. Okay? Now, third thing is existence of additive identity, meaning that there exists a zero matrix O such that A plus O is equal to A. Okay? It's a null matrix. Existence of additive inverse for every matrix A. There exists minus A such that A plus minus A is equal to zero matrix. Okay, matrix zero meaning that A plus minus A would give you a zero matrix with all elements is equal to 0. Scalar multiplication. This is the process of multiplying each element of a matrix by a constant number called a scalar. A is equal to Aij, Mn, and K is within R. Okay, so then Ka is equal to K times Aij. So you have K is the scalar number multiplied for all elements between I equal 1 to M and J equal 1 to N. Okay, I referring to the row index and J to the column index. So let A be equal to 2 minus 1, 0, 3. Then you have a scalar K equal 4. Let's multiply A by K. So 4A is equal to 4 by 2. Then 4 minus 1, 4 times minus 1, 4 by 3 and 4 by 0, which is equal to 8 minus 4, 0, 12. Properties. If K and M are scalars and A, B are 2 matrices of the same size, first of all, we have a distributive over characteristic over matrix addition. So K times A plus B is equal to K times A plus K times B. Second, distributive over scalar addition. So K plus M times A is equal to K times A plus M times A. Third, associative with scalars. So K times M times A, with K and M both are scalar values and A being the matrix, is equal to K times M together, then the product of those two multiplied by A gets us the same value as multiplying M times A at first, then multiplying MA with K. Okay, so they are all equivalent. Now, for compatibility with identity scalar, so 1 times A is equal to A, meaning that when you multiply A with an identity matrix, I, having only the elements of the diagonal ones and the rest are 0, like the remainder elements are 0, so 1 times A is equal to A. Matrix multiplication combines 2 matrices to produce a new matrix. But it's not just element by element multiplication. It is defined as if A is equal to a set of elements or numbers Aij, meaning that each number, each element of this matrix has an index I for its row position and J for its column position, existing in or within an M by N matrix, meaning it has M rows and N columns or columns. B being a matrix, also the same thing, so it has a set of values, each one having an I row, or like it is located on a specific row indexed by I and a specific column indexed by J, and having n rows and p columns. Okay, so it is not necessarily of the same size of A. Then the product C is equal to A cross B is an M cross P matrix where each entry is, okay, this is what I mean by M cross P. So the byproduct or the product of these two matrices generates a new matrix C, which has M rows and P columns. Okay, so M rows, the same number of the rows of A, and P columns, so the same number of columns of P. Okay, where each entry is Cij is equal to sigma k equal 1 to n aik times b kj. Okay, that is row of A times column of B. Condition for multiplication: the number of columns of the first matrix, okay, should be equal to the number of rows of the second matrix. So give you an example. Let's say you have A is equal to 1, 2, 3. B is equal to 1, 0, 1. Okay, so A times B is equal to, you have this, okay, multiplied by this. Yeah, this element multiplied by this. So the row element multiplied by the column element, which is 1 times 1 is equal to 1, plus this, which is 2 multiplied by this, so 2 times 0, 0, plus this, which is 3, correct, multiplied by this. Okay, so the third element, or the element of the third row multiplied by the element of the third column from the second matrix. So plus 3 times 1, which is 3, is equal to 4. So A times B is equal to 4. Okay, and the size of this matrix would be n, okay, M times P, which is the number of rows here times the number of columns. You have actually, yeah, no, not exactly that, but you see you have one column and one row. Okay, one column, yeah, exactly, you have one column and one row, correct? So 1 by 1 is equal to 1, so you have only one element, one row and one column, which is 4. This is how we evaluate the multiplication of two matrices. Another example to make it clearer. So let us suppose that we have two matrices, A and B, A having 2 rows, 3 columns, and B having 3 rows and 2 columns. The number of columns in A should be equal to the number of rows in B, so that the two of the matrices can be multipliable. So there's a condition that dictates whether we can multiply these two matrices or not. Let us notice something. So you have the number of columns or columns within A, which is equal to 3, is equal to the number of rows in B, which is 3. So 3 columns in A is equal to 3 rows in B, which is 3. Hence, we can multiply both matrices. So we have 1, 2, 3 columns and 3 rows here. 1, 2, 3 rows. So multiplication is possible. Let us multiply. So C is equal to A cross B is equal to 1, 2, 3, 4, 5, 6 multiplied by 7, 8, 9, 10, 11, 12. Okay, this is how we multiply. So for the first row within the first matrix and the first column within the second matrix, notice something. Where do they cross? Okay, so the multiplication of these two should give us an element, okay, a value, which will have the position of first row, first column, correct? Because we are multiplying the first row and this first column. So this value should sit on the first row and the first column of the new matrix. Okay? So let us multiply. It is equal. So C11, you see? C11, which is the first entry, or C of first row and first column, is equal to 1 times 7, correct? Plus 2 times 9, so plus second element multiplied by second element in the row multiplied by the second in the column, plus third element multiplied by the third in the column. Okay, so plus third element within the row multiplied by the third element within the column, which is equal to 7 times 8 plus 18 plus 3 times 11, which is 33, is equal to 58. Now, okay, let us multiply for C12. Okay, so first row, second column. Okay, so we are figuring out what would be the value on this position. Okay, at the first row, second column. So, which is designated as C12, first row, second column. Okay, so this is the first row, this is the second column within the second matrix. They intersect at this position, which means that would be C12, or the element at the first row but at the second position within the matrix. Okay, that would be the position. So C12 is equal to 1 times 8 plus 2 times 10 plus 3 times 12, which is equal to 8 plus 20 plus 36 equals 64. Okay, now, and notice something, by the way. So far you have 58, which is C11 that we've gotten previously, and C12, which is 64, which is the product of this row to the second column of the second matrix. Okay, first row of the first matrix multiplied by the second row of the second matrix, and 64 sits at the first row of the result or resulting matrix and its second column. This is how we are figuring all of these out. Okay, this is how we analyze it, and this is how we position different values. So C21, okay, C21, now we multiply the second row of the first matrix with the first column of the second matrix. So the result should sit at second row, first column, correct? So this would be the second row, first column, correct? That would be its position. So C21 is equal to 4 times 7 plus 5 times 9 plus 6 times 11. Okay, so 4 times 7 plus 5 times 9 plus 6 times 11 is equal to 28 plus 45 plus 66 equal 139. Then finally, C22, which is multiplying the second row of the first matrix times the second column of the second matrix. So the result should sit at the second row, second column, correct? Second row, this is the second row, and this is the second column. So let us check it out. So 4 times 8, which is C22, okay, second row, second column, equal to 4 times 8 plus 5 times 10 plus 6 times 12, which is 32 plus 50 plus 72 equal 154, and this is the result here. So this is the matrix, and the result or the final matrix would have the same number of rows. Okay, so the number of rows for the resulting matrix C would be the same number of rows for A and the same number of columns for B. So number of rows for A is 2, correct? And the same number of columns for B, also here you have 2 columns. So it would be 2 by 2 matrix, having 2 rows and 2 columns. Properties of matrix multiplication. First of all, it's not commutative, meaning that A multiplied by B is different than B multiplied by A. It is, however, associative, so A times B times C is equal to A times B times C, or cross, should I say, A cross B cross C. Distributive over addition, so you have A times B plus C is equal to AB plus AC, and A plus B times C is equal to AC plus BC. Then multiplication by identity, so you have AI is equal to IA equal A, where I is neutral. It is the identity matrix, having only ones within the diagonal, and all the other elements are 0. Zero multiplication, where A times a 0 matrix would give you always 0. Okay? Whether you multiply A by a 0 matrix or a 0 matrix by A, it gives you the same result. Let's multiply C by D and D by C, okay? Like C cross D and then D cross C. With C equals 0, 1, 2, minus 1, 3, 0, so 2 rows, 3 columns, and D, 3 rows, 2 columns. Number of lines is in C is equal to the number of columns in D, so MC is equal to ND, hence they are multipliable, okay? Or, yeah, when you say the number of rows, or sorry, the columns, number of columns in C is equal to the number of lines in D. It's the same thing. Okay, so you can decide whether they are multipliable or not if the number of lines in C, which is 2, is equal to the number of columns in D, which is also 2 columns. So MC is equal to ND. A11 is equal to, okay, so the element that will sit on the first row, first column, is equal to the product of the first row with the first column, giving us 0 times 2 plus 1 times minus 3 plus 2 times 5, okay? So minus 3 plus 10 equal to 7. That would be the first element. Then, first row, second column would give us the value at the second, the first row, second column. So, which is C1, 2, okay? First row, second column is equal to 0 times 1 plus 1 times 4 plus 2 minus 2, which is 4 minus 4, is equal to 0. Okay? I hope it's clear. And you go from there using the same method. Okay? So it gives us 7, 0 minus 11 minus 11. The resulting matrix is an M by M matrix, which is the number of lines within the first matrix, which you see, or in the same way, that's the same number of columns in D. Okay, so it is 2 by 2 matrix. The number of lines in D is equal to the number of columns in C. Okay, now for D multiplied by C, which is the inverse here, it will give us a completely different matrix. Okay, so D times C, you have number of lines at D is 3 lines. Okay, so D times C would give us a 3 by 3 matrix, which is the case as you see here. Okay, so D times C is different than C times D. The transpose of a matrix. Okay, transpose of a matrix is formed by interchanging the rows with columns, meaning that you flip the rows, all the rows become columns. Let us expand on that. So A is equal to Aij Mn. Transpose of a matrix At gives us Agi or Aj. So we flipped the elements. Okay, so the element that used to be on the first row, second column, has become seated at the second row, first column. Okay, so to put it in a more simplistic way, in other words, the element in row I, column J of At becomes seated at column I and row J. Okay, so we flipped I and J. We exchanged the column and the lines. Example, let A be equal to 1, 2, 3, 4, 5, 6. So the line simply becomes the column. So this first row becomes the first column, and the second row, which is 4, 5, 6, becomes the second column. It's like turning this matrix row by row in 90 degrees, okay? Clockwise, except, okay, so 1 to 3, you have turned the 1 to 3 90 degrees, so it became 1 to 3 as a column instead of a row. The same thing for the second row, so 4, 5, 6 has been turned 90 degrees, so it becomes a column, okay, of 4, 5, 6. This is how transposition works. Square matrix, if A is square, M equal N, AT has the same size as A. Symmetric matrix, AT is equal to A. When you have a symmetric matrix, it doesn't matter if you transpose it, the transpose would still be equal to the original matrix without transposition. Skew symmetric matrix, which gives us AT is equal to minus A. Okay, it flips the signs. Properties of a transpose. For any matrices A, B of compatible sizes and scalar k, double transpose would give you back the original matrix. So A transpose the first time, AT, okay, then you transpose it the second time, it goes back to its original shape. Okay, why? Because you flipped the row to a column, then you flipped it back to a row, so you get back to the original matrix, which is A. Sum transpose, which means that A plus B, the transpose matrix of A plus B, is equal to transpose of A plus the transpose of B. Scalar multiplication, which means K times A transpose is equal to K times the transpose of A. Product transpose, so A, B transpose is equal to B transpose times A transpose. Okay, you flip the order. Inverse transpose for invertible matrices, so A minus 1. T with IA minus 1 is the invert matrix, is equal to the transpose of A inverted. We will get to some of that later, okay, in an expanded manner. Symmetric matrix. A symmetric matrix is a square matrix that is equal to its transpose. This is what we mean by symmetric matrix, okay? Like AT, meaning the transpose of A, is equal to A. This is a symmetric matrix. Conditions, of course, it must be a square matrix having the number of rows equal to the number of columns, or M equal N. And that's the first condition, okay? And the elements should satisfy Aij should be equal to Agji. In other words, a number at, for example, okay, to give you a simplistic example, let's say you have a number at the second row, third column, okay, third column, it should be equal to the number of the third row, second column. Okay, so Aij is equal to, should be equal to Aji. The number of I row j column should be equal to the number on the opposite side or at the j row I column. Okay, so let's see it here more clearly. So you have here 2, 3, 4, 2, 3, 4, 5, 6, 6. Okay, this is the element at the second row, first column. Okay, is it equal to the element at the first row, second column? Yes, 3 equals 3. Okay, so 6 here is at the third row, second column, correct? Is equal to the number at the third column, but second row. You see what we're doing here? Okay, so to put it also in another way that can be more simplistic, so for example here, A13 is equal to A31. The number at the first row, third column, this is the first row, third column, 4, okay, should be equal to the number at the third row, first column. This is the number at the third row and first column. 4 is equal to 4, okay? So, in other words, and this is how we put it even in a more like a geometrical, visual way that can be simpler to look at. You see here the diagonal. The diagonal for this matrix to be symmetric should act as a mirror, meaning that you see these opposing numbers from one side to the other of this mirror-like diagonal. These values should be equal. So you see 3 is equal to 3. 4 at the lowest left edge should be equal to the 4 to the value at the upper rightest edge, okay, to the highest right edge. And you have 6 is equal to 6, okay. Here it doesn't count because this is the diagonal, so hence this is a symmetric matrix, okay. So we've explained it in multiple ways. At first, AT should be equal to A, meaning the transpose of this matrix should be equal to the original matrix itself, the matrix itself. Okay, it should be a square matrix with m equal n, the number of rows is equal to the number of columns, and the elements satisfy aij is equal to aji. So the value of a number at the I row j column should be equal to the number of the j row I column. So another example, you have the value here at the first row second column is equal to the value at the second row first column, okay. And the diagonal acts as a mirror again, where you have values from each side of this mirror, from the upper or lower side. They are symmetrically equal. 3 equals 3, 4 equals 4, 6 equals 6. Any square matrix M can be expressed as the sum of a symmetric matrix S and a skew-symmetric matrix K. Okay, so M can be rewritten as S plus K, where S is equal to M plus MT, or transpose of M divided by 2, and K is equal to M minus transpose of M divided by 2. If you add them together, you notice that the transpose of M cancel out. You are left with 2M divided by 2, correct? Which is M. So it is a different way of rewriting what a matrix would look like. So S is equal to M plus transpose of M divided by 2. K is M minus transpose of M divided by 2. If you add them together, transpose of M cancel out on both sides. You are left with 2M divided by 2, or M, because 2 cancel out as well. The identity matrix, also called the unit matrix, is a square matrix with ones on the main diagonal and zeros elsewhere, denoted by IN, where N means or refers to the size of the matrix, okay, being N times N matrix. So if N equals 3, we are referring to a 3 by 3 identity matrix. If it is 4, you have a matrix, an identity matrix with 4 rows and 4 columns. So let's say we have I3 here with ones on the diagonal and having a size of 3 rows and 3 columns. AI is equal to IA equal A for any compatible matrix A. It is symmetric, so transpose of I is equal to I. Determinant det of IN is equal to 1. It is always non-singular, invertible, and IN minus 1, meaning the inverse of IN, the inverse matrix of the identity matrix, the inverse of the identity matrix is equal to the identity itself. We'll get to what an inverse of a matrix means. Zero matrix, the zero matrix, also called the null matrix, is a matrix in which all elements are zero, denoted by 0 m times n, with m, n are the size of this matrix, should be the same size of the matrix that we're adding to or multiplying to. So mn here in this case, they are 2, 3, or 2 rows, 3 columns. Properties, it acts like 0 in a matrix addition, so a plus 0 is equal to 0 plus a equal a. It's null, it doesn't change anything. For any scalar k, O is equal to O, so if you multiply a 0 matrix by k, it gives you 0. It remains 0. In multiplication, a times 0 is equal to 0 if multiplication is defined. and 0 times A, or O times A, O being the 0 matrix, is equal to O, okay? So it destroys every other element within the other matrix. Just like among natural numbers when you are multiplying by 0. It's working in the same manner. Okay, compute the product between these two matrices. You have I2, I2, A0, I2, B0, I2 for A equal 2 minus 1, 3, 4, B equal 1, 0, 5, 2. Okay, so you have two identity matrices within the first. You have to the left, this is the first identity matrix, okay, of size 2 by 2, which is 2 rows, 2 columns. And this is A here, which is 2 minus 1, 3, 4. You have another identity matrix on the lower end, which is 1, 0, 0, 1. And of course, what remains would be 0. And here you have also I2, I2. You have B matrix, which is 1, 0, 5, 2. And 0, 0, 0, 0. You multiply them together and you get this matrix 1, 0, 3 minus 1, 0, 1, 8, 6. Okay, 0, 0, 1, 0, 0, 0, 0, 1. It is an upper triangular matrix. Compute M by N. Okay, so let us compute M times N. Two matrices happen to be square matrices of size 3 by 3. So, okay, N times N. Let us at first multiply the first row with the first column. What would be the index of the result of this multiplication? That would be a number sitting at 1, 1. First row, first column, correct? Equal to 2 times 1 plus 0 times 0, which is 0, plus 1 times 2, equal 4, and it needs to sit where? At the first row, first column, which is here. Then for the second, okay, so first row, second column, the element would be A, 1, 2. First row, second column, correct? Okay, is equal to 2 times 2, which is 4, plus 0 times 1, plus 1 times 0, which is 0. So this is equal to 4, okay? Sitting at the first row, this is the first row, second column, okay? Now, you go over all the elements in the same way to fill in M times N matrix, to fill in the result. So let us choose like a fringe position. Let's say the third row, and yeah, let's multiply the third row and the third column. That would be A, 3, 3, the element sitting at the third row, third column, correct? Which is equal to 4 times minus 1, or minus 4, plus minus 2 times 3, which is minus 6, plus 4 times 5, which is 20, equal 20 minus 10 equal 10, correct? And that would sit at the third row, third column. Okay, so this is the third row of the matrix and the third column, this position, and it's equal to 10. This is how you evaluate the product of two matrices. Okay, prove A times B transpose is equal to BT times AT, meaning that we need to prove that the transpose of the product of A times B is equal to transpose of B multiplied by transpose of A. Let us check at first A times B. A times B is equal to, okay, this is easy. You can pause the video and try to figure it out. So 2 minus 1 times 1, 5. Okay, so 2 times 1 plus minus 1 plus, plus minus 1 times 5, which is 2 minus 5, or minus 3, sitting at the first row, first column, okay? Then, first row, second column, you have 2 times 0, okay? 2 times 0 plus minus 1 times 2, correct? First row, second column, which gives us minus 2. Then, second row, first column, which is 3 times 1 plus 4 times 5 equal 23. And finally, second row, second column is 3 times 0. Let me clear it up. 3 times 0 plus 4 times 2, which is 8. Okay? And this would be the element A22 equal 3 times 0 plus 4 times 2 equal 8. It would sit here. Now, the transpose of AB is equal to, you simply flip the column into row, so and row into column. Okay, so minus 3 minus 2, or like, yeah, you see minus 3 23, you flip it 90 degrees anti-clockwise, or the way that you like to do it. Okay, so let us keep the original way. Actually, this is more fitting for me. So the column becomes row and row becomes column. Okay, so whatever way you want to do it. So minus 3 23, that was column, becomes a row. Then minus 2 8, this was a column, it becomes a row. Okay, minus 2 8. Okay, great. So let us now evaluate the transpose of B, transpose of A, and multiply them together. Transpose of B is equal to 1502. Okay, 15. So the column becomes a row. 15. You see, we flip them 90 degrees anti-clockwise, and 02. 02, which was a column, becomes a row. Same thing for A. Then we multiply BT times AT, or the transpose of B multiplied by the transpose of A. So what you get is minus 3 23 minus 2 8. Okay, hence AB transpose, or transpose of AB, is equal to transpose of B multiplied by transpose of A, or minus 3 23 minus 2 8.